Howdy folks, welcome back to Professor Carbon. In this video, what we're going to do is go over an interpretation of a fairly complicated NMR. In this particular case, it's actually going to be an amine containing starting material. And as always, what we're going to have to do is propose a structure based on the experimental data that we're given. And thankfully, we're given the proton NMR or the hydrogen NMR, the molecular formula, the IR, and the carbon-13 NMR. So let's dive in and see what kind of clues we can come up with. So the first thing let's just do is take a peek at the molecular formula. And the reason for that is the molecular formula lets us calculate the degrees of unsaturation. Now this is C10H15 with 1 nitrogen. And what I like to remember is nitrogen kind of brings with it its own hydrogen atom. So when calculating the degrees of unsaturation, we will look at it as if it were a formula of C10H14. Now, if you recall your degrees of unsaturation, in a saturated alkyl chain, every carbon is a CH2, and then there is a cap on the end, 1H for this side and 1H for this side. And so I try not to worry too much about the exact formula for degrees of unsaturation. I just try to remember what it's representing. Okay, so if we had a C10 chain, C10, we would expect there to be 20 hydrogens then in the chain for all of our CH2s. And then we would add to that 1H on both sides. And so we would expect that there would be a combination of 22 hydrogens in the fully saturated C10 molecule. We only have 14 that we're going to consider. So 22 minus 14 is going to be 8 that we're missing. So we're missing 8 hydrogens. That is, if we took our actual molecule and added H hydrogens to it, it would be fully saturated. Now, each pair of missing hydrogens, we're going to divide this by 2, and so we'll have 4. Each pair of hydrogens is going to be are central to our degrees of unsaturation. And you can kind of remember that because a double bond is 1 degree of unsaturation. And of course, if you hydrogenate a double bond, you add 1 hydrogen to both sides. So it takes 2 missing hydrogens to make 1 degree of unsaturation. And those degrees of unsaturation can either be rings or double bonds. And so that gives us some clue as to what's going on there. All right, so we're going to have to account for 4 degrees of unsaturation in this molecule. So that's our first clue, and we can get there without even looking at any of the principal data. Now, when you're given an NMR like this, what I tend to do is to try to scan it for anything that kind of just jumps out at me. And one of the things that jumps out right off the bat is this nice cluster of signals down at 5 hydrogens. And that is going to have to be a phenyl ring or a benzene ring with 1 substituent on it. And that is really good news because that benzene ring has 3 double bonds and a ring in it. And so right off the bat, all 4 of our degrees of unsaturation are going to be the fault of that benzene ring. And so we're done with that part of the problem. Let's just take a minute and scroll down to the carbon NMR and double check that. And so in our benzene ring with 1 substituent on it, and so I'm just going to redraw that here for a second. Remember, we're going to have 1 carbon here. I'm actually going to switch to yellow, a second carbon here. And then these 2 carbons are going to be the same because, again, the benzene ring can flip over. And don't be caught up by the resonance structures. So remember, because we're looking at the resonance hybrid in the NMR, it's going to be a mixture. And I'm just going to go back to, well, I'll use black here. There. And so I have a green, yellow, red, and black carbon. And so I need 4 carbons in the aromatic region. And so anything above, roughly 110-ish is going to be in that region. And conveniently enough here, I have 2 carbons that are short and then 2 carbons that are tall. And those tall carbons are going to be roughly about double the height of the small one. And so those are going to be the black and red carbons, and then the green and yellow carbons will be the other 2. Because I've looked at a bunch of NMRs, I can probably guess that that one will be the green one. and this one will be the yellow one. We have more complicated NMR experiments to show that definitively, but for now, we're not too worried about it. The basic thing that's important here is that we do have a number of carbons that match our initial hypothesis that this blob for 5H's up here is indeed a phenyl group. So that's also good because it takes into account a large percentage of our carbon atoms. So that benzene ring, if we just subtract out what's left from our molecular formula, so C10H15N, and now we're going to subtract from it C6 and H5. And so overall now we only have C4H10N to worry about. And so that is a much simpler problem than what we initially started with. Okay, so let's start looking at our other clues. Right off the bat here, we have a nice doublet for 3H's. And that is interesting because the peaks there, oh, and we have another nice peak here for 3. So that looks like a nice big tall singlet for 3H's. And those singlets for 3H's, that's got to be a CH3. And this doublet has got to be a CH3. And not only is this any old CH3, if it's a doublet, it's got to be a CH3 next to one other thing. And so that's kind of very convenient for us to think about as well. Okay, so how can we put these pieces together? Well, we're going to have 1H here. And by the way, there's a nice expansion. And so that's got to be that one. That looks pretty broad, and it's roughly in the range where we'd expect. So let's make that our NH. Like so. And then we have a lot of gobbledygook, And that gobbledygook, if we look at the expansion here, this is going to be a complicated splin pattern. But this pattern over here is one that we've seen before, or at least hopefully you've seen before. These are going to be doublets of doublets. And those doublets of doublets look like they're coupled to each other. And so what I mean by that is this distance looks like it's this distance, and they both have roughly the same kind of difference in heights there. And so those are going to be a CH2 unit that is next to a chiral center. In that chiral center, because these two are talking to each other, right, they're splitting each other into a doublet, that means that adjacent center is only going to have one hydrogen atom. And this is going to turn out to be very convenient for us because now we have this multiplet, but we also have this that has to be a CH over here next to that methyl group. And so if we put all of these pieces together, this has to be a CH2 next to two things, but only one hydrogen. And then this phenyl ring has to be broken off. And so if we just connect all of these bits, so this could connect to this signal, and then that could connect to this signal, and then that could connect to this signal. And so all in all, what that then can look like is something along these lines. And that's cool because I think it all matches then. So let's just take a minute here and try to identify what all of the peaks can be. So the methyl group, continue over here, is going to be this methyl group, that triplet. And the reason for that, of course, is it has a chemical shift in our nitrogen region. It also then has to be one of these carbons over here. And so I'm going to guess it's going to be that carbon. Now that is going to be cool because that matches the chemical shift and the integration and the splitting pattern. And then we already have our phenyl blob that we talked about earlier. So at least we confirmed that a couple of times. And now let's just work our way through all of the hydrogens in the backbone here, just as a double check. Okay, and so the red methyl group has to be a doublet, and it should be really, really upfield. And so indeed we have that here. We have a doublet for 3 hydrogens, and it is going to be split again into that doublet. And not only that, it's going to be right around 1 part per million. And so that's perfect. The green one here, now that's going to be a multiplet. It should be a quartet because of this, and it should be a doublet there and a doublet there. So technically it should be a quartet of doublets. And so that is a pretty complicated splitting pattern. And so I think we're cool calling that one this multiplet here. Let's drag that back down. And that chemical shift also matches. So it's pretty close to that methyl group, the nice tall one, and it's going to be in that range where we'd expect an alkyl nitrogen atom to have its adjacent groups. Now, these two are going to be the next more complicated one there. And remember, they're going to have to split each other, and then they're going to have to be adjacent to one additional hydrogen atom. Not only that, they're going to have chemical shifts about 3.5 that we're going to have to explain somehow. So let me go over here. It's going to be those. And the reason that chemical shift is downfield is because it's next to the benzene ring. And so remember, in our toluene molecule, these show up right at about 2.2. And so they're dragged downfield by virtue of being next to that benzene ring. So I think that all checks. Now, some of you may be wondering why these two hydrogens over here show up differently. And the best explanation I can give for that is if we look at the dihedral angles between all these groups. And so let me just put a blue dot, and then I'm going to use the green dot. And so the green dot is going to be back, green in back, and then we'll put the blue dot here. We can put that phenyl ring up, and then we can have our blue hydrogens over yonder. And then if we look at the one in back, we're going to have a CH3 coming off, and then we're going to have an NHCH3 coming off, and then we're going to have that green hydrogen that's kind of hanging out. And the reason that these are different then is because this blue hydrogen sees a methyl or an amine, and then this one sees a H in the amine. And so there's no way to turn this projection where both of the blue hydrogens see the same two groups. And so they're actually different, and we call this distereotopic. And it's because we have this pesky stereogenic center right next door. All right, so that sums up this video on how to interpret the NMR data for this particular compound. And hopefully you'll tune on back in to Professor Carbon.